Hey there, welcome to Introduction to Chemistry. As implied by this title, this video is meant as an introduction to chemistry for people who are completely new to the subject or just looking for some solid review. In this video, we're going to be discussing the stages of matter along with the classification of matter. So let's get into it. So the first thing we're going to look at here is this very common diagram you'll see in nearly every introductory chemistry course, and it discusses the classifications of matter. And before we do that, let's discuss what matter is, the top thing right over here. And in chemistry, there are three main phases in which you will see matter, which are going to be the solid, the liquid, and the gas phase. All right, and the best way to envision the properties of each of these phases is to use an example. So let's use an example of water, right? So example being water. And what is water in the solid phase? Water in the solid phase, as you should know intuitively, is going to be ice. So I'm going to draw a diagram of a quick ice cube. And one thing you can notice here is that this ice cube has a definite shape. What that means is that the particles inside the ice cube are very compact. They're packed very well and very tightly together. And if you want to write this in a chemical way, you can write the chemical formula for water, which is going to be H2O. And at the bottom here, this little subscript is where the form or the phase of the matter is denoted. And it's going to be solid. So S for solid. So that's what an ice cube is going to look like. Next, we can look at a liquid. Right? We can look at a liquid. And this is going to be a bowl. And inside here is going to be some water. The same thing, is the same chemical formula. But this time, it's water, but it's in a liquid phase. So we're just going to draw a little L here. And as you can see here, the particles aren't as tightly compacted as they are in the solid, because liquids aren't as tight or rigid as solids are. So that's an important observation to make there. And next, let's look at gases. Gases are pretty difficult to draw or just envision in general, so I'm just going to make a quick cloud. All right, and that's going to be H2O in the gas phase. All right, so these are the three phases, and if you look at gases, they're very dispersed. They're the complete opposite of solids. Solids are very structured and rigid, and gases are very, very dispersed, and that refers to the particles inside each of these phases. So the main trend you need to note here is that solids are very, very tightly compacted. Liquids are a bit on the medium end of it. They're a mixture of the tight compactness of solids and the very loose dispersed matter of gases and how far the particles are in gases. All right, and all these observations can be quickly noted down in like a really quick table. So I'm just going to draw that. And that's pretty much all you should really be comfortable with when it comes to solid, liquid, and gases. So let's draw that table here. So volume, shape, and we're going to have S for solids, L's for liquids, and G's for gases. All right, and we can use these examples to fill in this table. So do solids have a volume? Well, in this particular instance, we had a cube. And from math class, you know that you can calculate the volume of the cube. So yeah, it's true. Solids do have volumes. Does it have a shape? Well, as you mentioned earlier, in this particular instance, it does have a shape. It's the shape of a cube. So we can put a check mark right there. Do liquids have a volume? Well, you can think of this intuitively as well. If you go to the grocery store and you buy, a 25 milliliter can of, Canada Dry, that is the volume of the liquid. So yeah, it does have a liquid. But does liquid have a shape? I mean, think about that. If I were to put liquid in this container versus liquid in the same amount of liquid in this container, the shapes are a bit different. Even though it's the same amount of liquid, liquid does not have a definite shape because it depends on the environment in which it's placed, right? So for that reason, liquid is a bit flowy and shape-shifty, so it doesn't have a definite shape. So that's going to be an X right there. And we're going to be looking at gases. Do gases have volume? That is a bit of a trick question there. The question here should be, do gases have definite volume? And the answer is no. Gases exert pressure on the confines in which the gas is in, but it doesn't have a direct volume, a definite volume that is, all right? So it does not have a definite volume, and nor does it have a definite shape, because if you think about it, well, just intuitively, you can't really describe the shape of a gas. It's a bit it's a bit tricky to visualize, and for that reason, it doesn't have a definite shape, nor does it have a definite volume. All right. And another thing that we should be familiar with is the way that we transfer from a certain phase to another phase. And this becomes really important in units like kinetics, where we apply heat changes. So let's try and make a little triangle diagram, I think is probably the best way to do this. So we're going to have solids up here at the top. Solids. And then over here we can have maybe gases. Okay. And over here we could have liquids. And let's start off with the ones that are a bit more intuitive. All right, so how do you go from solids to liquids? Well, if you think about it, in the particular instance of an ice cube over here, you go from solid to liquid by melting the ice cube. So that's the process. It's just called melting. So melting is how you go from solids to liquids. And this isn't only applicable to water, it's applicable to really any kind of substance. All right, and then how would you go from liquids to solids, right? How would you go from liquids to solids? Well, when it comes to water, what you do is that you'd freeze the water, right? And it turns into ice. There's a more chemical name for freezing, and we don't typically use the term freezing, we use the term fusion, all right? So it's synonymous with freezing, but the proper terminology is going to be fusion. So from solids to liquids, it's called melting, but from liquids to solids, it's called fusion. So now let's focus on this connection here, from here to here, and from here to here. All right, and liquids to gases. That's a bit interesting. One way you could think about this is liquids to gases is vaporization. When something vaporizes. So when you take maybe a drop of water and you expose it to high temperature, it's going to vaporize into gas. That's what the process is called. It's called vaporization. Vaporization. Right? And if I were to go from gases to liquids, what you can do here is something called condensation. And you may see this on tree leaves, for example, is when gases, they condensate and they turn into water, and you see this little water droplets hanging off leaves, and that process is called condensation. All right, these are just terms that you should probably know, and they're applicable to a large part of chemistry here. And we're going to draw this last two-way street here. And we're going to go from gases to solids. And this one is probably the least, intuitive, from gases to solids, because you don't really see it too often. And the term here is actually called sublimation. So sublimation, from gases to solids. And from solids to gases, it's called deposition. It's called deposition. Right, and from the solid to gas ones are the ones that may require some memorization, as the other ones do come pretty naturally. But this is sublimation, and this is going to be deposition. All right, so those are the basic phase changes and the phase changes that you should know, and everything to do with phases. So let's get on to a practice problem I think we have. And here it is. So for his 5th grade science project, Carter demonstrates compression on both 25 grams of ice and 25 grams of water vapor. Which sample is more compressible? And I gave you the definition of compressible here. Compressibility is defined as the capacity of something to be flattened or reduced in size by pressure. Okay, so one thing you should note here is that the amount of substance is constant, but it doesn't even matter, because what we're asking for here is to use our knowledge of solids, liquids, and gases, and the compactness of solids, liquids, and gases. So when you compress something into pressure, it would be most effective to compress something if the things in the particles were very far apart. Why? Because if they were very close together, say very, very close together, as they are in a solid, it offers more resistance to the pressure. It's not going to compress as easily. It's a bit stronger, right? But if it's a bit more dispersed, as is the case in gases, there's a lot of empty space here. There's a lot of empty space between these molecules. And what the pressure can do is that it can use that empty space and exert pressure on it, hence compressing the substance, right? So the more heavy, more space between particles equals higher compression. The more space between particles equals a higher compression, and for that reason, since gases have more space between their particles than solids do, the 25 grams of water vapor, which is actual water and gas, is going to have a higher compressibility. So therefore, 25 grams of water vapor is more compressible. Is more compressible. Okay, so hopefully that made sense. So now we can look at the other parts to see how matter is classified. So the other parts of this diagram. So let's go in this direction first. So we'll go here. We'll go into the pure substances direction. And pure substances have a definite and constant composition. That's what characterizes pure substances from mixtures. Now what that means is that, well, it has a definite and constant composition. So let's use an example here. An example of a pure substance would be something like sugar. And in chemistry, you can express sugar or glucose as this, C6H12O6. That's the chemical formula for glucose, and it's a pure substance, and it's made from a definite and constant composition. For example, if I were to make some compound with, C5H14O3, you wouldn't have sugar. You would have some other substance. So to have sugar, you must have this constant composition of these constituents and this ratio. So that's what characterizes a pure substance. From here, pure substances branch off into both elements and compounds. And what elements are really the building blocks of pure substances, and they're composed of a single type of atom. Now, in this example here, we looked at C6H12O6, and carbon, C, is an example of an element. Hydrogen, H, is also an example of an element. O is also an example of an element that represents oxygen. So C, H, and O. Those individual constituent parts of glucose are elements, and they're composed of individual carbon atoms, hydrogen atoms, and oxygen atoms. There is no such thing as a glucose atom. There's only the atoms that are made up of elements, so carbon, hydrogen, and oxygen. All right, and the other part of pure substances are compounds, and compounds are pure substances that can be broken down chemically and are consisted of elements. So think of it as, elements make up compounds. And an example of compound is what we originally used here. C6H12O6, this is an example of a compound, and it is the compound of sugar. So elements, they kind of make up compounds, and compounds can be chemically broken down into elements. So it works both ways. All right, so now let's try and explore this section of it, which is going to be mixtures. And mixtures is a physical combination with no constant composition. Here, there was a definite constant composition, so definite, and here there is no composition. So that's the main difference there. And mixtures can be further broken down into either homogeneous or heterogeneous mixtures. And homogeneous mixtures, or solutions, is a common term you will hear that's synonymous to that, are uniformly distributed. All right, they're uniformly distributed, typically one phase of matter, and visually they're the same throughout. On the other hand, heterogeneous mixtures are where the composition varies, and it's typically multiple phases. An example of a homogeneous mixture could be something like something that is uniform, something maybe like an energy drink, where there are multiple parts to it. However, they're all in the same phase and they're all distributed evenly. On the other hand, an example of a heterogeneous mixture can be something like, ice cubes in water, because obviously they're different phases, as ice is in solid, and they kind of separate from each other. They're not uniformly distributed. There's no chunks of ice in the middle of the water, if you know what I'm saying there. All right. And if you want to look at it from a particulate representation, something that's very basic, but it gets you the idea, let's draw some particles here. All right. And we'll get rid of this one actually. So we're going to have 4 particles here. And for homogeneous mixtures, say these are different particles. These form different phases, right? There's like a barrier here in a sense. While as in heterogeneous mixtures, the two different substances, the black and the white particles, are mixed evenly, while in homogeneous substances, the black and the white particles sort of form some kind of a barrier. Okay, So now let's work on this last practice problem over here. Kyrie drinks a bottle of water, but his friend Kevin pours some oil into his bottle as a joke. Is this new mixture homogeneous or heterogeneous? So let's start off with a diagram. So this is going to be Kyrie's bottle here. And there's going to be some water. I think we can use the same color. So there's going to be some water. And Kevin wants to throw in some oil. So let's see what that turns into. And you have, this is what it turns into. And what's really important to know here is that oil and water do not mix. You may be able to see that in everyday life, but they do not mix because they're very different and very distinct in densities. Oil is a lot less dense than water is, so it's going to rise on top of water, right? And you may be wondering, well, they're all in the same phase. Well, not really. Yes, they are both liquids. However, they do form distinct stages. This is one stage up here, and this is another stage. And what is characterized by multiple stages, multiple phases, which of these is characterized by multiple phases? It's going to be heterogeneous substances. So for that reason, this mixture is an example of a heterogeneous mixture. Thank you for watching. Hopefully you learned something new, and please like or subscribe.